Now I want to talk about another tool that is available to astronomers for determining the composition of objects that are very, very distant from us, that all we can see, all we have to tell us about those objects is the light that they emit. When we look at a hot, solid object, an object that's opaque, that we're not seeing through it, we're just seeing the light given off from its surface and from its collective motion of the molecules and atoms that make it up. What we get is this full rainbow of light. If we look at light that comes to us from the sun, we get this thing called a black body spectrum. If we look at, though, a diffuse gas, a gas that is transparent, that when we're looking at it, we're not seeing the bulk thermal radiation of the atoms and molecules as a whole, we are looking at the light given off essentially by individual atoms or individual molecules in the system. What we see is something more like this. We see a broken spectrum consisting of very narrow, bright lines. And by the way, all I mean when I say spectrum is a rainbow of light. So a hot, diffuse, transparent gas that's giving off its own light, like the gas in a fluorescent light. This classroom that I'm in right now has fluorescent light tubes in the ceiling. How do they work? They're tubes full of gas. You run electricity through them that excites the electrons. It causes the atoms to give off light. And there's a phosphor, like a sort of white powder painted on the outside that re-radiates that light. So that's an emission spectrum. Another place that you'll see an emission spectrum is something like a neon sign that gives off light of a particular color. The complement to that emission spectrum is something called an absorption spectrum. If we take gas and we shine white light through it, a cold gas that's not being excited to give off its own radiation, what we see is the spectrum of light that we pass through it has certain frequencies or wavelengths of light absorbed from it. We call this spectrum that's interrupted by black lines where the gas has absorbed some of that light of particular wavelengths, an absorption spectrum. So a cold gas which is not glowing on its own, it's not emitting visible light, that is either reflecting light or light is shining through it, we'll see an absorption spectrum. So these are the different kind of spectra we can see when we look at different types of objects. Here is an object in space called the Horsehead Nebula. It's actually several objects. Here's a star with some gas around it. That gas is glowing due to the light of the star. Here is a black cloud of gas that is obstructing your view of the gas behind it. If we look at these objects with a spectroscope, we will see different sorts of things. If we look at the light passing through this dark gas, we will see certain wavelengths of light absorbed by the gas in the nebula. That is an absorption spectrum. If we look at the light being emitted by the gas that's being caused to glow by the heat and light from the nearby stars, we will see an emission spectrum. That spectrum will tell us something about the gas, just like this spectrum will tell us something about the gas, and they actually tell us the exact same thing. What they tell us is what that gas is made of. You can think of these emission spectrum lines and these absorption spectrum lines as carrying information the same way that a barcode on a product that you buy at the store carries information. The position of those lines corresponds to different energies, and those different energies correspond to the energy levels of the electrons in the atoms that make up that gas. So an emission spectrum and an absorption spectrum are sort of mirror images or inverses of one another. Hydrogen gas, for example, when it emits light, if that gas absorbs light, it absorbs those exact same frequencies or wavelengths of light. Every element in the periodic table has a unique spectral signature. If you take that object, you make it into a gas, you run electricity or heat it up through the gas, it gives off light. If you look at a quote-unquote neon sign, an old-fashioned neon sign, first of all, only the red ones are neon signs. The green and blue and yellow ones are some other kind of gas that's not neon. By the way, nowadays a lot of quote-unquote neon signs are not really neon signs. They're just LEDs that are different colors. A real neon sign is a tube filled with a particular gas. Each of those gases has a unique spectral signature. So neon looks red because it has a bunch of spectral lines in the red end of the spectrum. Some different gas, sodium, has two very, very bright lines in the yellow part of the spectrum. Every different gas has a unique spectral signature. Every element in the periodic table has a unique spectral signature. We can take every element in the periodic table, put it in a tube, turn it into gas, put it in a tube, run electricity through it, and measure the wavelengths of the spectral lines that it gives off. Then, if we look out in space and see those same spectral lines with those same wavelengths or those same frequencies, we can identify which chemical element is responsible for giving off that light. That means that spectroscopy, the science of studying atomic spectra, gives us a tool for determining the composition, the chemical composition of very, very distant objects that we can only see the light that comes from. So if you open an astronomy textbook and it tells you the sun is mostly hydrogen and helium, how do we know that? We know that from looking at spectral lines. If you open up an astronomy book and it says the atmosphere of Saturn's moon Titan has a lot of methane in it, how do we know that? We know that by observing the spectral lines of light reflected off of Titan's atmosphere. So we don't need a sample of Titan's atmosphere to bring back to the lab and analyze it. All we need is the science of, or the tool of, spectroscopy. It's worth spending a little bit of time asking the question, why does every element in the periodic table have a different atomic spectra? What is the cause for these spectral lines? This could get really, really complicated if I decided to spend an hour explaining to you how it works, but I'll give you a sort of cartoonified version of the reason for this first. First, here's a cartoon picture of the atom. There are protons and neutrons in the nucleus. There's electrons that in some way go around the nucleus. Do not take pictures of atoms like this seriously. This is not what an atom looks like. You can think of this as a map of an atom. Think about a subway map if you've ever been on the DC Metro or the New York City Metro. A subway map shows you different colored lines that represent the train lines. They're all perfectly straight. All the stations are evenly spaced. That's not what the real subway lines look like. If you go underground, you will not find the train tracks painted green and yellow and blue, right? You will not find all of the stations exactly equally spaced from one another. You will not find the tunnels to be perfectly straight lines. That subway map is a diagram to tell you where the stations are and which trains go there. Okay? This cartoon of an atom shows you what the parts are, protons and neutrons in the middle, electrons out here somewhere, and how they are related to one another. It's not to scale. Protons and neutrons are not little balls. They're not red and blue. Electrons are not orbiting the nucleus in a little orbit the way planets orbit the sun. That is not what happens in an atom. It is much, much more complicated than that. But that doesn't stop us from sometimes drawing atoms this way schematically to get the point across. When an electron in an atom absorbs energy, it can move to a higher energy level. The energy levels in an atom are what we call quantized. An electron in an atom is only allowed to have certain energies. It's much like the situation of a piano. Okay? The notes on a piano are quantized. You can play a C sharp, a D sharp, an E, an F sharp. You cannot play a note in between an E and an F on a piano. That note simply does not exist on a piano. You can play a note between an E and an F on a trombone or on a violin or on some instrument that allows you to make the pitch whatever you want it to be. By the way, this is why a violin is harder to play than a piano, because you can be between the notes on a violin. You can't be between the energy levels in an atom. It's not allowed. Okay? You can be a C or a C sharp or a D, but you can't be in between there. And the spacing, the actual specific energies of the electrons in an atom depend on how many protons there are and how many electrons there are. And since every different element in the periodic table has different numbers of protons and electrons, there are different energy levels for each different atom. So an electron in this atom, by the way, this atom would be helium because it has 2 protons in it, is allowed to jump from here to here if I give it a little bit of energy, but it's not allowed to jump halfway there because there's not an energy level there that it's allowed to have. It can absorb a little bit less light and go from level 2 to level 3. It could jump from level 1 to level 2, and those are the only jumps in this cartoon atom that this electron is allowed to make. So those are the only 2 energies of light that this atom is allowed to absorb. When the electron moves down, which it will spontaneously, just like a ball rolling down a hill, it will spontaneously at some point move down, it will emit those same energies, those same wavelengths of light. So if I shine white light on a tube full of these atoms, it will absorb the frequencies or wavelengths that correspond to the sizes of its energy jumps. If I run electricity through that atom, kick all the electrons up to the top and let them roll downhill, they will give off those same frequencies, those same wavelengths, those same colors of light. And again, since every atom has different numbers of protons, different numbers of electrons, different energies in the atom, the spacing of these energy gaps is different for every atom in the periodic table, which means that the frequencies and wavelengths of light emitted are different for every atom in the periodic table. By the way, there are other types of spectroscopy that are useful at different wavelengths than visible light. If you look at the nucleus of an atom, the protons and neutrons can actually change their energies as well, and that generally gives off much, much higher energy light into the X-rays and gamma rays. That's called nuclear spectroscopy, looking at the energy given off by the nucleus. If you look at a molecule, say this is a picture of a CO2 molecule, carbon dioxide, the atoms that make up the molecule can actually oscillate, and the energy of those oscillations is quantized. And so this molecule only gives off certain wavelengths of light corresponding to the energy levels of this oscillation. Those wavelengths tend to be in the infrared, and so molecular spectroscopy in the infrared can tell us something about the molecules, the combinations of atoms that make up a say an atmosphere. How do we know that Mars has got carbon dioxide in its atmosphere? We know it from molecular spectroscopy. So we are not hampered in astronomy by not being able to travel to the outskirts of the solar system or to other galaxies in order to see what things are made out of. We can very easily see what things are made out of just using light. And that is a huge stroke of luck, you could almost think of it, that light carries information about an object's composition, because otherwise we would not be able to tell what anything in the universe was made of.